Thank you. So I will present this talk here about Herglotz functions and the way we use Herglotz function to solve some, what I think, practical problems. I'm from Lund University in Sweden, and this is joint work over the years with quite a lot of different people that I just mentioned up here. So the application that we are looking at is really to figure out what is the best we can do when we want to build something. And we want to build, I would say, fairly complicated structures. So one case here is, for example, antennas, which maybe can look like this. We can make some periodic structure in this high impedance surface. And the question is, if you have a given design space, so you have some height, you have some available material, you just ask, what is the best performance that we ever can get out of what we would like to do? So that's what we solve. And we then look at different structures. As I mentioned, this periodic structure, it's one application. Scattering, absorption, extinction. So you can look at a case where you would like to, for example, maximize the absorption in some particle when you illuminate it with some electromagnetic field. Maybe you would like to minimize it. You would like to do RCS and hide something. It's a similar problem we look at that. Composite materials homogenization, I will not talk about here, but it's a big part of this conference. So that comes into the same functions from a different perspective. And many of the bounds that we have in these areas, so really the fundamental limits, what can be done, are either based on this holomorphic function, so the Herglotz-Nevanlinna functions. So that is why I think that's a big part and why I like them a lot. It's a nice mathematics, but also very many practical applications there. And in these cases, the Herglotz-Nevanlinna functions fundamentally comes from the assumption of passivity. So we have something that doesn't really produce energy. And I come back to a strict definition of this. Intuitively, it means that we have a system which is causal, and you don't get more signal out and in. But then, of course, we need to define what that is. From this, we can then define some rules, and from that, we can get some bounds. The other alternative is to do optimization. So in some ways, very, very different perspective, and it solves the same problem. Sometimes it leads to the same results. Many times they're almost complementary. And I will a little bit show what I find as challenging here and what I think that we can do. So the first thing with Herglotz-Nevanlinna function, and the reason why I think these are the best functions ever, this is passivity. And the thing that we have is passivity from what's called a scattering perspective. I will start with that. So here we have a definition of something. We measure something and we have a system which is on convolutional form. So time translation and invariant, and it's linear. That's what we have. And then we have some input signal and we have some output signal, and this is always greater than equal to 0. That defines that it is passive. So we don't care what's inside of it. We only care about the signal we can send in and the signals we can get. That defines this. So we can think about send some wave here into something, you get something out. And then the beauty of this is that this defines now a holomorphic function, which in this case maps here. Now I took a right half plane to a circle, I could take the upper half plane, and I'm a little bit confused. So sometimes I do Herglotz-Nevanlinna function, sometimes I do positive real. So rotate is 90 degrees. They're the same function. And in these cases, we then have these mappings here. And those are, of course, very much related to the Herglotz-Nevanlinna functions because we can map the unit circle to another half plane. And then we will have the class. The direct class to get the other function is called admittance passive or impedance passive. And it's a slightly less intuitive formulation that we have here. We have an input signal, we have an output signal, real part, integrate over all times, and this is always greater than 0. It should always be for all functions here too. So all possible input signals. This should be valid. That defines then what we have an admittance passive system. Directly, this is intuitive again, voltage here, current into a resistor in some ways. And this defines now our positive real function, what I draw, or a Herglotz-Nevanlinna. So this is where I find almost all of these functions. I know other people in this audience, they find it from solution of some PDE. And you can do that too, and they shows up almost everywhere, which I find is one of the beauty with this function. But here I really come from this, if we have something which is passive, which in many cases things are in our daily life. We look at a system, yeah, we don't get more energy out of it. Okay, it will be passive. Maybe that's the only thing I know. But suddenly you know a lot, because it means that you have one of these functions, which means we can then use the mathematics of that to tell us something about the system without going into too much of a detail. So the mathematical definition here of passivity is conceptualizes the intuitive statement of having less energy in than out in some ways. And it looks simple. It's also sometimes confusing. I can say in many cases when I do this, people say, oh, my cup of coffee here is passive. Of course it's passive. It doesn't produce energy. But maybe I cannot use it in a passive system, because it depends how I illuminate it and how I get my signals out. If I look at the monostatic scattering of this, it's typically not passive, but it's the same object. So it's really the system where we use it that creates passivity. So this then goes to our definition, our favorite functions. And since it's a meeting here about these Herglotz-Nevanlinna functions, of course we have to define them. So now I went to the upper half plane. And then we have the mapping here from the upper half plane to the upper half. So that defines our function with many names, which amazingly shows up almost everywhere. So it's beautiful. And there are scalar versions, matrix versions, and there's operator versions. So it exists many, many different types, with of course then many different applications for them. I'm mainly focusing here on the scalar version because that's the one I can use. Sometimes we need the matrix version to construct the scalar version. So we can jump between them. The operator version, myself find it difficult, so I usually approximate it and it becomes a matrix and I'm kind of happy. And it's common, as I mentioned, in many areas of mathematics, physics, and engineering. They shows up almost everywhere. And they are then fundamentally linked to this function of passivity. So if you have this LTI system, you have passivity, you have one of these. Which means I would say we basically always have these functions. Of course, we should study them a lot. We should really understand what they are. And they can be done then for many different types. Here is one very, very early reference. The mathematics of the passivity in these was basically done in the 60s. So it's well known what it is, and we really have these properties. So we have a one-to-one mapping. Where do we then find them? So if I look at practical cases for me, I can have some material here. It can be homogeneous, it can be inhomogeneous, it can be periodic. I can then define some signals coming in. I have some reflected, I have something transmitted. These are typically passive systems. This will be the scattering passive system. I send the signal to this slab, I get something back. I don't get more energy back, which means I will have passivity. I can look at material models. So here I have a map from the electric field to the D field. This will be now a passive system. I don't have a material that produces energy in this case. So immediately I will know that my material model, the permittivity here, frequency-dependent permittivity, can be anisotropic. It will be a Herglotz-Nevanlinna function. So I have the model class for them. I can look at scattering. And as I mentioned before, scattering can be tricky. If you look at backscattering, like monostatic RCS, typically not passive. But if I look at the forward scattering, it is passive, at least in electromagnetics. If you do it in acoustics, it's not. Because in acoustics, you can actually have a material which increases the wavefront speed. And then you basically lose causality. And if you lose causality, you lose passivity. So it depends where you are to get these things. You can look at state space model. So a very common model in system theory. It shows up state space models. You can look at the integral equations that we are using. They forms a method of moments matrix. We get these positive real or Herglotz functions. So the Herglotz-Nevanlinna functions are then generic models for all of these LTI systems or passive LTI systems. And then bounds that we derive based on these functions will immediately apply to all of those. And that's where we suddenly can say something of doing something with some complicated material here or periodic structure. Because I take one property of it, I use the mathematics, and then it applies for it. That's why it gives us the powerful theory of this in some ways. And the way that at least we've been using it here has been gone down to what's called some integral identities or sum rules. So these Herglotz-Nevanlinna functions, they satisfy a few mathematical, properties. So if we have a Herglotz-Nevanlinna function, they always have this assumption because it could be that it disappears. But in many cases, they have like one pole. And if they have that property that they locally looks like a rational function, at least to some order, we have some expansion coefficients here of these ones. It can be at 0, it can be at infinity. They typically come from the complex plane. Along the real axis, we don't really know what these are. They can behave very, very strange. But from the complex plane, they have some regularity. And if they have this property here, we can write up some integral identity of this, that we integrate the imaginary part of this Herglotz function. The imaginary part is always positive or non-negative. We weight it with something here, depending on the order of these coefficients. We take some limits here, and that's equal to the difference between the coefficients. That's what we can use. Which means that if I now go back to what I said from the beginning, I use this function to study one of these systems. The only thing I need to know are these coefficients. And if I know the coefficients for the system, these will be equal. This area that I have here with this integral will be equal for all systems with the same asymptotic. That will give me a bound for everything you can build, because the statics is very well behaved. We typically know what's happening with it. Dynamics, basically anything can happen, except that the area is conserved by this Herglotz-Nevanlinna function. So that's what we will use. So if I take just one example to show how this could be used. So if we take a structure here, so you see some incident wave here, transmitted wave, reflected wave. This is how you can build it. So this is build and measure too. And then you ask a question. Over what bandwidth is more than 80% of this incident power transmitted through this perforated screen? Hey, that looks complicated. I mean, I don't know what screen I built. How can I know over what bandwidth you get more than 80% to pass this? You basically need to measure it. Or you need to do a detailed simulation and say, at this frequency it goes through, this frequency it's blocked. Because the periodicity here is some kind of filter. So sometimes it goes through, sometimes it's blocked. But the sum rule, that will actually tell us that the total frequency, so the spectrum, where more than 80% goes through, is conserved. And it's only given by a static property. Isn't this amazing? I mean, how could we in some ways believe this could happen? It's fascinating, and that's this mathematics of this Herglotz-Nevanlinna function. So if we see if we would like to analyze these ones, what we do is that we write up the transmission coefficient. That's a passive system. We send something in, we get the transmission coefficient. Of course, it's passive. You don't get more power that goes out. You don't gain time. And then you use, in this case, that this is a thin screen. And that actually means that it's even restricted here to a smaller circle. So all transmission coefficients live not on the unit circle, live in a smaller one. That's a symmetry that as much is reflected as transmitted. And then you can take and map that one. So you make some conformal mapping here, and you map that to the right half plane. You take your mathematics there, analytic function. You can, of course, do a mapping to that half plane, which is analytic. And suddenly I will have a Herglotz function. Now I have a Herglotz function. Then I can use the asymptotics of that, and I can write up an integral identity for it. So let's do that. We take the Herglotz function we constructed here, we compose it with a new Herglotz function. Because if I have a Herglotz function, maps the upper half plane to the upper half plane, take a new Herglotz function, of course you still map the upper half plane to the upper half plane. So now I have a new function here, which is this one, which I don't say what it was. I compose it with this. You can see it's not rational. What you have here is only that it's 0, some spectrum, and then 0. Now I probably did a positive real there, but it doesn't matter. So you take that one, you compose it, and this is what you get. So you get an identity here that you integrate this very odd thing, which I don't say what it is, and it's equal to gamma, which is the polarizability of this structure, which basically says how it can separate charge in some abstract way. You have some delta, which sets the threshold for this one, and you have the cross-sectional area. Wholly depends on anything. We know what it is. And the fascinating thing is that this composed function here is either 1 if the transmission is greater than my threshold, or it is identically 0. That's how I construct this. And it's from a holomorphic function, which goes between 0 and 1. But you can do that with these ones. And since this has these properties, you integrate over all wavelengths, of course I get the area of this one when it is greater than, in this case, the threshold level. So here you see an example. This is 80%. You can see the simulated in this case is transmission. When it goes above 80%, it goes up to 1. And I know the area under this dashed line that sits there. Of course, it comes a lot here, and it comes the major part. And this is now normalized, so of course this was 80% of what you can ever get when you change that geometry, unless you increase the polarizability. That's the only thing you can do. And I mean, it's magic. How is it possible? The mathematics here in some way says that whatever I build here, it will be constrained by this static little thing. And we could maybe think about it in some ways, but it measures when the transition is more than 80%. Of course, I can put 90%, it doesn't matter. A certain threshold level I can get in, and I get this out. I find it fascinating. I mean, I don't understand how it is possible, but this is, of course, possible. So we can derive many of these bounds here, and we typically derive them from passivity and causality in these cases. So as I mentioned, we can do it for antennas, we can do it for periodic structures. Many of these cases can be done. And the bounds are always coming from this type of identity that we have. It can be formed in different ways. You can do it by adding some poles and so on. But I think the most powerful of these ones is with adds a pole at 0 because it gives statics, and statics we know what's happening. So we can do that. And the bounds are then illustrated by some area. So now I had extension of a sphere. And in some ways what it says is that your curves can never be above the green area here or this green here. So it gives some average response. You cannot go over that. But of course it says absolutely nothing what's happened at the fixed frequency. We don't know what's happening. And the analytics here cannot give it to us because we have not succeeded. So it misses something. So it's very simple, closed form expressions based on an identity, which is extremely good. But it's not valid for saying the maximum of something. If I would like to know what is the maximum of this one, this cannot answer it. It has really nothing to do with this static value. It depends on something else. And it's incredibly hard to include additional information. What I mean with that is that this thing I have here with this area is the same in the two examples as I have here, gold and silver. The green area is the same. It's independent of the material. But of course, the response depends heavily on the material. So maybe I will do something better by saying, you have gold. Can you do something better if you only have gold? Or maybe you can mix gold and silver. Maybe you can do it. To my knowledge, these methods don't have a chance to do with that. So then we need to do something else. So we need other techniques for single frequency bounds, and bounds depending on additional information, for example, material parameters. It could be that you build an antenna, you're not allowed to build it everywhere and so on. Then you need something else. These analytic functions don't really do it. So another technique of doing the same, that is to use optimization. So if I model my problem, so now I do very abstract formulation here, this is my entire physics. I just write it up that I can construct this linear mapping because it's a linear model. I have some unknowns I call I, and I have some excitation I call V. If you know circuits, this is the voltage and the current. But of course, if I do scattering electromagnetics, the same. If I do acoustics, it doesn't matter in this case. What I would like to do when I solve this is to compute the current, which computes some functional I'm interested in. And what I do now is I say, I would like to maximize this one. I'm interested in how much can I get from this one. Okay, let's maximize it over all currents. Doesn't really give you anything. So what you do is that you take the first constraint you have up here, and you basically reformulate it. And it looks like, okay, this is harder. But of course, now it's not a linear constraint. Now it was not, the geometry model. Now it's something that conserves energy. That's the interpretation of this one. And then I solve this one, and then I get up some optimal currents, and then of course I get up my optimal value of this one. Unfortunately, this is really hard to solve. So you take one more step of this, and what you do is you form a dual problem. And if you do the dual problem, you rewrite this with this Lagrangian typically, or some other dual formulation, and you solve that problem. And if you solve that problem, you get some Lagrange parameters, and then you use that the solution to this problem is always less than this. Which means I can figure out what is the best you can do by solving an optimization problem. Of course, now I have a new path into this. And it's relatively easy to solve this, especially when you have a few unknowns here. Here I had 2, it's complex valued. So that's easy to solve. Much, much harder if you have more of these constraints. Sometimes it's possible, sometimes it's not really possible. And there are many results the last years on antennas and scattering that's doing. So it's something that maybe we can use. And one example where it can be used is, for example, these cases where I showed again some gold sphere here, and you would like to know what is the best you can do for a given wavelength or frequency. Now it can solve that problem. The previous one can solve like the average response. Now I can ask it for this wavelength, what is the best I can do? And I can add it's gold, so I can get it out. And in this case, I solved this optimization problem here. We don't really say how we solve it, doesn't matter here, but we can solve it. And we can then compare with something that's realized. Those are dashed lines here. So you can see in these cases, we're actually not too far away from at least a structure that was easy to realize. So it really says something of how good you can do this. It's close to reality in some way. And we can do it for different sizes. For small sizes here, you can see the realization is actually on top of it. For larger structures, a little bit bigger difference. But the realizations here are layered structures. So maybe it was limited in the way we can actually build this. Building it is NP hard. That's a really hard problem. And what you can get out is then a given wavelength here. What is the best you can do? What is, for example, I think this extinction or absorption. How good can it be for different materials? So it can in some ways quantify. From this material you can do this. For this material you can do this. You can get things out here. And you can make a trade-off. You can ask, can you now switch between the maximum absorption and scattering? So if you build a structure, maybe you just want a lot of scattering, but not so much absorption. And then you can get some range here where you can actually build designs which perform something. And also this one you can solve with this. So in these cases, you get that all realization need to sit within these black curves here. Realized ones are these green ones. And of course, realizing them is really hard. Getting the bound is really easy. So we can easily get out something that we can do. And we can look at other things. You can do cloaking with these ones. So here you have cases where you would like to either, let's say, minimize the scattering. So you want to hide something. How good can you do that? And with given losses here, you can get some bounds and you can do some realizations, and it's not too far off. So we can do this one. I will just go through a few quickly here to come to the main part of this. You can do information of this. What is the largest capacity you can get? Again, we can formulate this as an optimization problem. It's just slightly more complex here, but you can do the same. You can solve also. We can solve almost anything in these cases of saying, a given geometry, what can we get out of it? But we are basically limited here to fixed frequency. That is the problem. So if we do this one, it's given for losses that we have here. We have some certain size. I have some structures. Okay, what can I get out? This is the sphere case here. If I add some other materials, they are similar in this scaling. The flat one's a little bit below, and the bad one is a little bit there. But we can say, how many degrees of freedom can it for given material or given losses in this? But what we cannot do is in some ways to add the bandwidth. So in the first method, I could do everything for bandwidth, and here bandwidth is really hard. So in some ways, I need to combine these two. I need to get something out of them. So the constraints we have to optimization produce bounds for a single frequency, and they're extremely powerful for that. And it's also often important to have good performance over a band. So I need to get that in. I need to get that formulation in. And some possibilities to do this. There are different ways of doing it. We can use these holomorphic properties, so passivity, and then I can combine them in some ways. And I can use that for extinction cross-section and for some other metrics. I can use what's called a stored energy, or what we will see very soon is derivative of the material parameters. And this is a classical approach. It works in antennas. And we can compute it from frequency derivatives here of basically the material parameter, which is a little bit what we had in the previous presentation, that this quantity shows up. That's why I'm curious about this one. Because we use it a lot. Sometimes it behaves good, and sometimes it behaves really bad. That is the issue with it. But that comes in there. And we can, of course, combine also the holomorphic properties with optimization. And we can add multiple constraints, because, of course, you can say they have constraints for different frequencies, and I have a multiple amount of constraints. People have tried to solve it. It's a lot of work. For example, Miller up here. But it's very, very hard to do in practice. It creates problems. So we will look at a simple case. I don't know if I'm out of time or very soon.
Yeah, a few minutes.
A few minutes, that's good. So the idea with this, I will just show what it is. So if we think that we have a single resonance, so I would like to have a large bandwidth. So if I take my system and it responds like this. So this is a cross-section, and here around a normalized frequency to 1, I have a large response. I would like to have a large bandwidth. I quantify the bandwidth with a parameter which is called Q. So basically 2 over Q is the bandwidth here, and now it's the fractional bandwidth because it's normal. That's what I get. And if I now say this is an Herglotz-Nevanlinna function, of course to this parameter I'm interested in, there is also real or imaginary part, and that has a slope. And of course at the resonance, it's negative. That's the problematic thing with this once again. That is always change sign around the resonances, so it's indefinite in this case. But the beauty of it is that I can look at this slope of these ones, and the slope that we have here is related to the Q factor. So in some ways, if I differentiate this Herglotz-Nevanlinna function, I get something that is related here to the bandwidth. So then I can get that in as a parameter that I can use. And higher amplitude in this model would then be also narrower bandwidth because the area is conserved. If you remember, the sum rule says that the area is conserved. So if I make it more narrow, it has to go higher. But I can normalize those. So we can use this slope as a constraint in the optimization as long as we have a Herglotz-Nevanlinna function. Because then I can say that I look at the single resonance model, I look at the slope of it, and I basically constrain that. Then I can get it in. So if we look at the extinction cross-section, it's unfortunately a little bit tricky to do it. This is an abstract way of writing it. So you have a product here with some currents, and you have some excitation V. This is just notation for it. And if you write that up, you have to basically invert this impedance matrix, and you can differentiate. And when you do that, you get a few unfortunate terms. So that's why I have to write approximately equal to, because actually you have some complex conjugates there that doesn't go your way. If it's small, they disappear. But if you take that out, you have a derivative here which is approximately equal to the derivative of the imaginary part of this matrix. And this is actually what we used in antennas for like 10, 15 years. So we used it a lot there. And it works really well on antennas. There we don't have really these approximations. They comes in from the scattering. If we look at an example, so we look at the extinction cross-section that we have here. We add these as a constraint. Okay, those should be maybe after each other. I relax this one, and what I relax it to is I say, I don't know what the material is, I only know the losses. And if I get in the losses here, I can write it as a convex problem here. And if you look at the result here, I get this blue line if I solve this one. Okay, it doesn't tell you anything. I have two dashed lines. The dashed line here is the sum rule, and the dashed line here is a maximum you can get from the single frequency one. It actually follows it quite. So it seems to give something that is quite good. And of course, if we then believe this will be the bandwidth, then you can just add that to your constraint of other parameters, where we don't maybe have the Herglotz-Nevanlinna property, because maybe I'm interested in absorption. Absorption is not the Herglotz-Nevanlinna function, unfortunately. So we can not use it there. Then comes the big question of this, and that is actually how do we compute derivatives? Because the derivatives don't behave well. It's typically indefinite. If we do this for highly dispersive media, the sign goes all over them. Then you can take a step and extending it to a Herglotz-Nevanlinna matrix function, a state space model for that one. And that you can differentiate. And when you differentiate that, you actually get a definite sign on it. If then this is a correct energy, who knows? I can say for a lumped circuit, it's exact. So there we can do it. So we need a few properties here. So we have a Herglotz-Nevanlinna function when we do the modeling. And the stored energy has been analyzed for the state space models. It's positive semi-definite material part, so we can add it in. We have one more part to take care of. We need a minimal realization to do it. You can have hidden states in these ones. The hidden states don't deal with you because it doesn't disturb you. You don't see them. They are hidden for you. So it doesn't matter what's happening. There are actually many, many open problems. A big one is that we have a time delay. Time delays don't fit this rational functions. So I hope I'm not too much over the time. So some conclusions here is that passive systems and Herglotz-Nevanlinna functions are the most beautiful functions for me. They work for almost anything we would like to do. We can do sum rules. We can do bounds from these weighted integrals. We get closed forms expressions for almost everything. Really analytic expressions. It's very, very hard to then change them. When they work, they work. When they don't work, they just don't work. Optimization problems are robust, so extremely general, easy to add information. Solutions from a dual problem, They are very good for single frequencies. They're very good for like one material case. There are promising approaches for bandwidth. I wouldn't say it's a solved problem in these cases. Another final thing with this is, of course, this is a meeting about this Herglotz-Nevanlinna function. And what I would find very, very interesting is to go slightly outside of that. Because in my opinion, we know 99.999% of everything with passive system and Herglotz-Nevanlinna function. Today, you're typically interested in something that do a little bit better than these bounds. When people understand this is limited, they're trying to figure out how do I break that bound. And they typically break one of the assumptions that we have. For example, time invariance. So you have a time varying system. To my knowledge, there doesn't exist any mathematical representation theory for us that are useful to say something. We have mathematics, we can simulate it, we can write models, but we cannot do anything that is close to what we can do with Herglotz-Nevanlinna. And I think this community could help, because I need them. I want to use them. I can maybe not develop them, but if somebody develops them, I can absolutely use them. And of course, some generalizations or generalization is to lose passivity, would be very good. Causality, another one, of course, nonlinearity and activeness. We need to move on in this model. Okay, with that, I hope I don't went over time too much. And if somebody has a question, maybe for the coffee break, I don't know. So, thank you.
Thank you very much. We have time for one or two questions. Yes.
Thanks for a very interesting talk, Mats. I guess I had a couple of comments. I thought it was very interesting, this connection with the slope and the Q factor. And it seems to me that in the quasi-static limit, where you're looking at small particles, that you could derive something in that direction based on composite materials, because composite materials correspond to sort of small particles, and using Herglotz-Nevanlinna things, you can relate that to the sort of slope. So anyway, we should probably talk about that. And the other question
I can just say that, I mean, I probably totally agree when you go to the material view of it. But when you look at, for example, a version of, say, antennas,
yes,
it's totally fine. We know what it is, and what it requires there is actually that the structure is sub-wavelength.
right.
So we don't need to go to something that's low frequency. We need to go to something that is less than the wavelength.
Yeah, but
So it's a wavelength-related stuff.
Yeah, that's what I mean by quasi-statics. And anyway, the other thing that may be interesting is that Owen Miller and collaborators have done some work on scattering cross-section bounds for particles, and it may be interesting to do a comparison if you hadn't already done that.
Yep, maybe we have, I don't know. Yeah.
Yeah.
Another question? So if you have no more, yes, another question. Aaron?
This is about the generalization here. Can you tell me maybe where the progress is with like quasi-Herglotz functions, and if that's been useful in this regards?
I think it's extremely interesting. I cannot say that it is so far useful. Now I sit on the two chairs that I think the mathematics is very interesting there. When it comes to really using it, I haven't seen a case where it really, what I would say, solved a practical problem. But I think it's the path that we need to go. I mean, we need to say something that we lose some of the properties and we actually get in something that still is useful. And to my understanding of it is that we need something that is closer to this representation type theorems that says every passive system is a Herglotz-Nevanlinna function. Okay, what is then when we took at this quasi version, then we go from the mathematics and we say, okay, let's take maybe a difference, let's do something with it. But what is the general physical system it models? And I think we need to do work there. And we need, in some ways, some understanding of what it means in physics or engineering problems to understand what is this class of problems. If I mention another one, time invariance, what is the problem with that? typically your Fourier transform is gone, which means that our life as an analytic function is difficult. But you can do perturbations, so you can look at single terms of that, and I think you can do something. And maybe that could be extremely useful, because in practice that's what we are doing, or what people who's doing that is doing. And they should have some analytic.
What about like gain, loss balance, loss and gain balance, PT symmetry, things like that? Have you explored those ideas?
Yeah, I think there's a lot of interesting things that can be done there. And of course, gain is going to an active material, and still you sit in this case, what does it actually model? Which I think we need to do work. We need better models for it.
Very short question. Is there like an extension like to the sum rules that you use when you know the low frequency and high frequency behavior of your Herglotz function that give you the moment of the imaginary part? When you have a Herglotz function with several variables?
I push that on to Anne-Marie. I can deal with one variable, and I try to understand two, but it's hard.